Hello everyone, I'm a TA for Computer Networking course, and today I will be giving a simple introduction on how to convert a standard HTTP web page to a secure HTTPS page. To demonstrate this, we will be working with the simple web application built with Python and Flask. As you can see, I've just started the web server. When we access the application, the first thing you will notice is the browser warning us that the site is not secure. This is a clear sign that our connection is running over plain HTTP. This means any data sent between our browser and the server, like a username and password, is unencrypted and could be intercepted by anyone snooping on the network. Our goal today is to fix this. We are going to secure our application by implementing HTTPS, and we will do this by generating our own self-signed SSL certificates using a command line tool called OpenSSL. All right, let's move into the hands-on part. In a real production system, you would never create your own certificates manually. Instead, you would request a certificate from a trusted certificate authority like Let's Encrypt, which is already recognized by all major browsers. But for this demo to better understand how HTTPS works, we will build our own small homemade CA. This will allow us to issue certificate ourselves and see how the pieces fit together. The first step is to create a root certificate authority. This is like becoming our own trusted entity for the purposes of this demo. First, we generate the CA's private key with this command line. This creates the file root.ca key. This will be the master key of our CA, the tool we use to sign other certificates. This private key is the most critical secret of the CA. It must always be protected and never shared. Next, we use the private key to generate the CA's public certificate. Think of this as the CA official ID card. When you run this command, OpenSSL will prompt you with a message. You are about to be asked to enter information that will be incorporated into your certificate request. These fields include information such as country, state, organization, and locality. For our demo, we will keep it simple. We will only fill in the locality name Korea and leave the other fields blank by entering a dot. This information becomes metadata inside the certificate. It identifies who the certificate belongs to and who issued it. Later, when the certificate is used in HTTPS, this metadata is also transmitted securely as part of the encrypted connection. At the end, this command produces the file root.ca_pen. This is our CA's public certificate, which others can use to verify certificates we sign. Now that we have our own CA, we can issue a certificate for our OAuth server. Just like CA, our server needs its own private key. This command line creates key PAM. It is the server's own secret key used to decrypt data sent by clients. Next, we generate a certificate signing request. Which is like an application form that the server submits to the CA. This server CSR file contains the server's public key and some identifying information like the server's domain name. It's the formal request asking the CA to approve and sign the certificate. Finally, we have the CA sign the request producing the server's official certificate. And next, this step combines the CSR with the CA signature, resulting in the file certificate PAN. This is the public certificate of the server. It will present to browsers when they connect over HTTPS. With these steps complete, we now have our homemade CA and our server's private key and signed certificate. These files are the foundation for enabling HTTPS in our Flask app. Now, let's see what is the main difference of HTTP and HTTPS. First, let's take a look at the main function of HTTP application. In the HTTP version, we simply call app_run method. There's no mention of security or encryption here. This means the server only communicates over HTTP. However, in the HTTPS version, you can see a key difference. We add an argument called S as a context. This is a tuple containing two files, the server's public certificate and the server's private key. Certificate PAM acts like the server's ID card. The server presents it to clients to prove its identity. Clients then use it to start an encrypted session. And key PAM file is the server secret. When the client encrypts the data using the server's public key, only the server can decrypt it with this private key. That's how sensitive information stays protected. So, by adding an SSL context, Flask doesn't just serve plain HTTP packets anymore. Instead, all communication is wrapped in TLS encryption. That means data like usernames, passwords, cookies, and session IDs travel safely across the network, hidden from anyone who might be listening in. Alright, let's start our secure server. Now, when we navigate to our HTTPS, we are met with this big privacy warning. However, this is not an error. It's completely expected and a key part of the running process. This warning appears because the certificate was signed by our homemade CA. not one of the major CAs that browsers trust by default. First, let's click these buttons to proceed. We can tell the browser to proceed anyway, but how can you prove our encryption is really working? We will use the developer tools. To open the developer tools, press F12 on your keyboard, and then click over to the security tab. But for now, we already see the security overview. This page shows our current security status. Here we can confirm that the connection is secure. However, you will also see the warning message because, as mentioned earlier, we are using a homemade CA. So, before we wrap up, let's take a look at what's actually happening when we load our HTTP and HTTPS pages. For this, we are going to use Wireshark. This is the Wireshark tool. Wireshark is a network protocol analyzer that lets us capture and inspect packets traveling between our computer and the server in real time. To focus only on our application traffic, I've applied the uh, simple filter here. Let's begin with the HTTP version first. When we access the HTTP page, the first thing we see in Wireshark TCP three-way handshake. This is where the client and server establish a connection before any data is exchanged. It starts with a synchronization packet from the client to the server, followed by a synchronization and acknowledgement from the server, and finally an acknowledgement from the client. These three steps of handshakes finished, the connection is ready to carry HTTP traffic. Next, we see the HTTP packets themselves. For example, uh, a get or HTTP slash 1.1 or 200 OK response coming back. If we inspect these packets, we can literally read everything inside the requested URLs, the headers, the content type, and even the HTML or CSS code returned from the server. This makes it clear that HTTP traffic is sent entirely in plain text. Anyone capturing these packets could easily read or modify the data. While HTTP is simple and fast, it provides no protection for the information being transmitted. Now, let's switch to our HTTPS version running on port 5002. This time, the Wireshark capture looks totally different. we see TLS with 1.3 packets instead of plain HTTP. First, we see a short TCP three-way handshake, synchronization, and acknowledgement. Right after that, the TLS handshake begins. We can spot messages like client hello and server hello, where the client and server agree on which encryption algorithms to use and exchange keys. Then we see change spec and application data packets. And from that point on, everything is encrypted. The data itself is not unreadable. We can see packets flowing, but the content is hidden behind the TLS encryption layer. This is proof that HTTPS is doing its job. So, to recap, we started with an insecure HTTP application. We created our own certificate authority using OpenSSL. It issued a signed certificate for our Flask server and configured the app to run securely over HTTPS. Then, we confirmed encryption in action both visually in the browser and technically through Wireshark. The HTTP packets were in plain text, while HTTPS packets were encrypted after the TLS handshake. This clearly shows the difference between HTTP and HTTPS at both the application and network levels. While the browser warning is expected with self-signed certificates, we have proved that real encryption is happening. With HTTPS, your user's data is private, authenticated, and secure. Thanks for watching this video. Thank you.